To begin this program, I want to demonstrate a very simple example of integer programming and use this to show you the main idea behind the branch and bound method. This is the problem I want to look at. So far, it's just an ordinary linear programming problem in two variables with three constraints. But I want to add an extra restriction. x1 has got to be integer. Now, it's a strange thing about integer programming problems that, although there's a lot of mathematical theory behind them, it turns out in practice that the method we use is childishly simple. It's based on one simple idea. We have a method for solving continuous linear programming problems, the ordinary type. This is the simplex method. And every integer programming problem has a related continuous problem. It's the same problem without the integer restrictions. It's quite likely that the solution to one is close to the solution to the other. So we begin by solving the continuous problem. That is, we forget about the integer restriction and we solve the problem. So that's the solution to the continuous problem, and not surprisingly, x1 has turned out not to be integer. It's 3 and a bit. So what are we going to do? Well, if we're going to get an integer solution, either we've got to forget about that bit and have x1 3 or less, or we're going to have to push x1 up and it's got to be 4 or greater. We've got two possibilities. We can look at them separately. Suppose we add the restriction that x1 is less than or equal to 3. Well, this gives us a new continuous problem and we can solve that. There's the solution, and it satisfies our restriction. x1 is integer and the value of the objective is 10.9. However, we said there were two possibilities. We've got to solve the other one. Remember, that was x1 greater than or equal to 4. Solve that. Another solution that satisfies the integer requirement. So there were two possibilities, and we've now looked at them both. The solution to our overall problem is the better of these two solutions. In fact, it's the second one I looked at, the one we've got on the screen at present.
Let's make sure that this works. Let's convince ourselves that we have a reasonable method of solving this problem. Because the problem only had two variables, we can look at the situation geometrically. The feasible region of the continuous problem would look something like this. But now we have the added restriction that x1 must be integer. This restricts us to points on these vertical lines. When we made the first attempt at our problem and solved the continuous problem, we got this solution, the continuous optimum. Unfortunately, you see, x1 has not come out integer. We're not on one of the vertical lines. So we restricted ourselves to two sub-problems. First of all, we said x1 has to be either less than or equal to 3 or greater than or equal to 4. By restricting ourselves to these two regions, we're not taking out any points on the vertical lines. So we first of all solved the left-hand region, problem corresponding to the left-hand region, and we got this point. We then solved the problem corresponding to the right-hand region, and we got that point. If we had more integer variables, of course, the problem would be rather more complex. But each step would still be similar to this. At each step, we would split the feasible region into two parts. Each part would correspond to a sub-problem, which we would then have to solve.
Keeping track of these sub-problems can be a difficulty with a larger problem. You can't draw the feasible region and tick off the bits as you look at them. But what you can do is imagine the sub-problems set out in the form of a tree. To show you how this tree works, I want to give you a second demonstration. In fact, it's the same problem, but I've got a different integer restriction. In this case, I want both x1 and x2 to take integer values. Well, as before, we solve the corresponding continuous problem. We get this solution as before. Now, neither variable is integer, so we have a choice. It's entirely arbitrary. We take one of the variables, say we take x1, we create two new problems and branch on x1. We now store one of these problems and we solve the other. Here's the solution, well, here's the new constraint and here's the solution. It's the one you saw before. x1 is integer, but x2 isn't. So what do? We branch on x2, create two new problems. We store one of them, and we solve the other. Here are the constraints, and here's the solution. Now that is an integer solution. It's the best integer solution we've found so far, so we call it the bound. At this stage we know that the solution to our overall problem must either be this current bound or must be one of our two stored problems. That's problems 4 and 2. So we look at the stored problems. We start by looking at problem 4. Well, that has these constraints, and here's its solution. Now, that's not an integer solution. x1 has a fractional value. So it looks as though we're going to have to split. But this is where the bound comes in. Look at the value of the objective. It's the same as the bound. As we work down the tree, we're steadily adding more restrictions. Therefore, we know that the further down we go, the worse the value of the objective is going to be. We can't do better if we go further. Therefore, we can forget about this whole side of the tree. We know that the current bound is going to be the best value we can find on the left-hand side. However, we've still got another problem. We stored problem 2. So let's solve that. Here's the new constraint, and here's the solution. Well, that's not an integer solution. x2 has a fractional part. So we have to branch on x2. We have two problems. We store one, and we solve the other. Let's solve it. Well, x2 is integer, but you can see that x1 has ceased to be integer. We've got to branch again. We store problem 8, and we solve problem 7. There's the restrictions. You see, those actually force x1 to be exactly 4, and here's the solution. Now that is an integer solution, and the value of the objective is better than the bound. So we've got a new bound, and we can forget about the current bound. At this stage we know that the solution must either be this current bound or one of the two stored problems, problems 8 and problem 6. Now, I'm not going to work through those last two problems. I think you can see what's going on. In fact, if you solve problem 8, you'll find it's infeasible. We put so many restrictions on it's become infeasible, and the same for problem 6. And it turns out that the overall solution to our whole problem is the solution up on the screen here now. x1 equals 4, x2 equals 3, and the value of the objective is 11.
So this is it. We've reconstructed that part of the tree which we went through, all the nodes we went through before we got to the integer optimum down here. Notice that in order to avoid having to explore large potential areas of the tree, we've used a number of stopping rules. These are computationally very important because they save us a lot of unnecessary calculation and so speed up our solution of the problem. The first stopping rule is fairly obvious. Once we reached an integer solution here, we obviously no longer needed to explore further down the branch. This then gave us a second stopping rule, and on the value of the objective function, once any branch deteriorated an objective value to this value of the bound, in this case 10, it happened here, we could terminate the branch again. The reason for this depends upon the observation that you'll notice here that as we progressively go down a branch of the tree, the objective function is getting worse. Now, we'd expect this to happen. The more we constrain a problem, the less well we'd expect to do. So this provides us with a useful stopping rule. A third stopping rule arises from a very similar reason. The more we add constraints into a problem, the more likely we are to make that problem infeasible. And this has in fact happened. It happened at 2 points. It happened here and here. We constrained the problem sufficiently here that it had no feasible solution. And so we can obviously terminate a branch when the problem becomes infeasible. So we solved the problem, and we got to the integer optimum down here. Incidentally, when we got here, we didn't immediately know it was the optimum. We had to go back and store and unstore these problems. These problems turned out to be infeasible, so we could immediately dismiss them. And we then knew that this was indeed the integer optimum. So we solved it with a tree with 9 nodes. Let's now think about how we might organize this calculation on a computer, this tree search on a computer.
For a computer program, I've got to think about the arbitrary decisions I made while I was doing my demonstration. If you remember, I made 3 types of arbitrary decision. First of all, when I got a solution, such as this solution here, where several of the integer variables hadn't got integer values, I had to decide which integer value to choose, which to branch on. That was the first decision. The second decision was when I generated a couple of problems, such as here I generated 2 problems, I stored one and I solved the other. That was the second decision I had to make. Finally, when I'd worked my way down the tree to a node like this one, I went back and took a program which I'd previously stored and solved that. And I had to make a decision as to which of the stored problems I wanted to solve. Well, these 3 decisions taken together are called the branching strategy. Clearly, as long as you work out all the branches of the tree, eventually you will get to the integer optimum. But the order in which you tackle the branches makes a big difference to the amount of calculation you have to do first. For my demonstration, I used a very simple branching strategy. I always branched on the first integer variable which had taken a non-integer value. Then, when I'd selected 2 problems, I stored the right-hand one, the greater than or equal to one, and I branched onto the left-hand one. So that was my branching strategy. For storage, well, for storage I used a strategy called last in, first out. Let me explain that to you. I began by generating 2 problems. I stored problem 2, solved problem 1. I then generated problems 3 and 4, stored problem 4, and solved this problem. I now had to take a problem out of store. So what did I do? I took out the one that had gone in most recently, the last one in. And that was the next problem that I solved. Okay, came back up the tree to here. Well, there's only one problem in store, so I solved that. Going down the other side, generated 2 problems, stored 6, solved 5. Down here, stored 8, solved 7. Well, actually, I didn't work out the rest of this demonstration, but had I done so, I'd have first of all taken out problem 8, that is the most recently stored problem. Then I'd have done problem 6. Then I'd have gone back to my store and I'd have found it empty. Well, for the store to be empty is a sign that I've looked at every possible problem. It's my stopping criterion. When I get an empty store, I know that the current bound is indeed the integer solution and I've solved the entire problem. The difficult thing about the branch and bound method lies in this branching strategy. There doesn't appear to be any simple strategy that works well for all problems. So what we've got to do is, as we look at each problem, we have to think about it and decide what strategy is going to suit that problem. Here's Paul with a rather bigger demonstration to show you some of the ideas involved.
Let's look at how a practical integer programming problem can arise. We'll first of all model a situation and then we'll try and solve it using the branch and bound method. The problem which we're going to look at is the margarine blending problem, which you've already met in Unit 5. This was the problem of how much to buy of these 5 raw oils and blend them together in order to make some margarine. The quantities of oils which we should use are represented by these continuous variables, x1 to x5. We now have an extra condition that if we have any fish in our blend, it's not possible to have soya or palm as well. This extra condition can't be modeled by conventional linear programming. This is a case for integer. We have to introduce some extra variables into our problem, some integer variables. These are 0, 1 integer variables. They can only take 2 values, 0 or 1, indicating the presence or absence of the corresponding ingredients. For example, if we have soya in our margarine, we want to make sure that D2 is 1. We have this situation. How can we express this in our problem? Well, it can all be done by this constraint. Let's think about this for a minute. If D2 equals 0, this constraint forces x2 to be 0 and forces soya out of our blend. On the other hand, if D2 is 1, this constraint simply tells us that X2 is less than 1,000, and we've purposely chosen this coefficient of 1,000 to be a known upper limit for X2. In fact, it's the vegetable refining capacity. As long as we choose this coefficient sufficiently big, we don't impose an unwarranted restriction on the value of X2. And in a similar way, we link D3 to X3 and D5 to X5. So we've now equipped ourselves with 3 0, 1 indicator variables indicating the presence or absence of these corresponding 3 ingredients. So now we're getting somewhere. Let's see if we can model this restriction, this logical restriction, using these 3 new variables. Then neither soya nor palm. In terms of our new variables, this is if D5 equals 1, then D2 and D3 must both be 0. The single linear constraint, this is a rather surprising fact. Let's check that this works. If D5 equals 1, that is, fish is in our blend, this margarine, or rather this constraint, boils down to D2 plus D3 plus 2 less than or equal to 2. The 2's cancel, giving us this, and forcing both soya and palm out of the blend. On the other hand, if fish is off, we get, substituting D5 equals 0, this constraint which allows us to have soya or palm or both. So this is it. By means of 3 extra 0, 1 variables and some more constraints, we've modelled our logical restriction. Everything's been put together here. We wish to maximize our revenue, which depends upon the quantities of the ingredients we use, X1 to X5, and the variable X6, the total quantity of margarine we make. These variables are involved in 5 conventional blending constraints, which were discussed in Unit 5. We've now added 3 more variables, 3 0, 1 variables into our problem, and linked them to some of the continuous variables. We've then imposed our logical restriction by this constraint. So this is it. A 9-constraint mixed integer programming model with 8 variables, and 3 of these variables can only take integer values.
I solved this problem on the Student Computing Service. Just for the sake of a demonstration, I used the same naive branching strategy as before. That is, I branched on the first non-integer variable, and I always branched to the left, the less than or equal to constraint first. Using this branching strategy and proceeding exactly as before, I ended up with the tree you can see here. That is, you see, I started off with the overall continuous problem. My branching strategy was to look at the integer variables in turn. Okay, D2 had an integer value, so I didn't branch on that. D3 had a fractional value, so the first branch was to branch on D3. Coming down the left-hand side, this was the first problem I solved. And eventually I generated all these problems. I got to 3 integer solutions, and the overall solution is in fact this one over here. Now, with the benefit of hindsight, it's fairly obvious that that was a bad branching strategy. For example, suppose I had entirely arbitrarily gone down the right-hand side first. Well, I'd have come down here and I'd have got to this integer solution very quickly. When I came down the other side, this first continuous solution is worse than that integer solution. Therefore, I could have stopped at that point and forgotten about this half of the tree. That's with the benefit of hindsight. The interesting question is, can we go back and think about our original problem and see if we can devise a better branching strategy without having to do all this calculation first?
Let's first of all look at our formulation. Our logical condition was expressed by this constraint at the bottom. An alternative way of doing this would have been to use the 2 single constraints below. Let's make sure that this works. If we have fish, D5 is 1, and our constraints become The ones cancel, giving us these constraints, which force both Sawyer and Palm out of our blend. So this is an alternative way of doing it. We can either use the constraint at the top, the single constraint, or we can use the two constraints at the bottom. Which is better? Well, we're going to experiment. We're going to replace the top constraint in our model by the two lower constraints and solve our reformulated problem. The key to everything is fish. D5, the indicator variable for fish, occurs in both our new constraints. It might seem more sensible to branch on this variable first. If we do this, there's some hope that we'll get to a good integer solution fairly quickly and therefore obtain a good bound on our objective, and this may help us to solve our overall problem rather more quickly.
That is exactly what happened. We solved the problem using the new formulation and this, we hope, better branching strategy. This is the tree we got. As you see, it's very much smaller. The reason is simple. We solved the continuous problem, here's the solution. Since d5 was not integer, we branched on that straight away. We came down here, d5 equals 0, no fish in the solution. And we got this integer solution straight away. On going down the other side of the tree, the first continuous problem we solved was worse than the current bound. So we didn't have to go any further. And we'd solved the whole problem just by looking at that very small tree. I wonder if you can see why Paul's new formulation was better than the old one. Well, we had two ways of handling the same thing, the top line and the two lines beneath. From an integer point of view, they're exactly the same. But there are fractional values which will satisfy the top line but don't satisfy the two lower lines. This means that when we embed our integer programming problem in a continuous problem, the feasible region of the continuous problem is smaller, and there's a better chance of getting integer solutions when we solve it. I think that's a lovely example of how the branch and bound method works. Okay, I know it's a very little problem, but integer programming problems have a habit of growing rapidly. Paul was telling me that he had been solving a problem very similar to this, only a multi-period problem spreading over 6 months, with logical constraints very similar to these. And when he solved that, he found he had to look at no less than 1,479 nodes of his tree. That was using a good branching strategy. I leave it to you to imagine what would have happened if you'd used a bad strategy.
There's